Hi, welcome back to my shed. In this video I'm going to show you how I made two chucks fit my lathe. But first I would like to say thank you to all subscribers to this channel. Your continued support is very much appreciated. And I'd also like to say, if you haven't subscribed yet, you could be missing out on latest videos or updates. I find swapping the chuck on my lathe to be a bit of a chore, undoing and removing three 14mm nuts whilst doing battle with the associated washers and at the same time trying to balance the chuck on the edge of a spigot. Having my fingers do the shuffle with a nut and washer in a gap that has scarcely enough room to pass a feeler gauge through is for me a bit of a challenge. For what? To use the 4-jaw chuck to do one operation and then have to swap it back again? Yeah, I know I could leave the 4-jaw chuck on and lose the 3-jaw chuck. And there's the argument that I should have gone for a lathe with a quick change chuck system. But you'll have to go to the website to find the answer for that one. But anyway, I like the convenience of the 3-jaw chuck offers, and I like to make things as easy as I can for myself. It was while I was struggling to find a wayward chuck washer that I saw the possibilities with double chucking. After all, it was quite a common occurrence when I was earning a living. The trouble with double chucking on a small machine is that the head bearings are not really capable of handling such a load. It was a spark of inspiration that got me thinking, well, that or I'd bang my head at some time. But what if the 4-jaw chuck had its own bearing and the 3-jaw chuck drove the 4-jaw chuck through it? Better still, what if it was reversible, so that the 4-jaw chuck could operate from both ends of the lathe? To be of any use, it has to be reversible. Not only that it can be driven by the 3-jaw chuck at the chuck end, but that it can be driven by an offset workpiece, for example, at the tailstock end. Obviously it has to be rigid, and it'll also need to be serviceable. That's maintenance, adjustment, greasing, etc. This, as you can see, is the standard engine lathe layout. And this is my plan. To make a pedestal hold some bearings that support a shaft, in turn supports and drives the 4-jaw chuck. The bearings I shall use will be type 32011, the same as the ones in the lathe head. The problem here is that the taper bearings would keep falling out or stick to the shaft every time I pulled the shaft out to change the chuck round. So I opted to fit a bearing sleeve that has to be pressed into place, and it's machined to allow the spindle to be removed and reinserted from either side without dislodging the bearings. But the spindle must be a push fit inside the sleeve. First I'll start with my usual material lineup with a bit of skip fodder. Despite having this material, I still had to buy some more, including a second 5-inch 4-jaw chuck and some bearings. This is a small length of tube that was once roughed out for something I didn't use. It's just over 60mm long. These two bits of angle iron are going to be the supports for the bearing case. If only that were possible. I've got to cut a scallop out of each of these supports. The base plate is going to be a bit of 20mm thick mild steel plate. It's only marginally thicker than the legs on the lathe's saddle. Using the lathe saddle as a surrogate base plate will enable me to easily set the required arc for the bearing cage. And what better to machine the arc than to use a milling machine boring tool. Fortunately, the saddle's got a couple of well-placed accessory screw holes. I can use them to clamp each support when I machine them. I don't know what I'd do without my hacksaw. I actually piecemealed these scallops so as not to go oversized with the bearing cage fitment. For every 1/10 of a millimetre too much, I would lose 2/10 off the top of the bearing seats, so I've got to be careful. The base plate you see here was too small for the task, so I swapped it out for a bigger piece a bit later. After welding the supports together, I used 2 jacking bolts to prevent the supports from squashing together in the vise while I machined them. I guesstimated that I'd got about 1/2 millimetre of room to play with on this bottom face, so after setting true I skimmed as little as possible off just to clean it up. The rest of the faces were just licked to dress them up purely for aesthetic reasons. It was just after this shot I welded the bearing cage onto the 2 supports. In order to cut the V-slots in the base plate, I had to be sure that the 2 slide faces on the main slides were in fact parallel and in line with each other. And using the DTI in this fashion indicated that I did indeed have an error. In fact, it was 0.075 millimeters over 125 millimeters apart. That's 3 thou. Using 2 parallels, a straight edge and a torch or flashlight, no error could be found. So I ran a DTI across the same 2 faces, but instead of moving the cross slide, I rotated the DTI about the mag base. That indicated that the 2 main slide faces were indeed parallel and level with each other. It turns out that the cross slide is about 2 minutes and 4 seconds of a degree out of parallel to the 2 bed faces. Another odd thing I found was that both V's were 94 degrees and not 90 degrees that I thought they ought to have been. Still, that could be accommodated. It's not going to stop the world turning, that's for sure. To be able to machine the base plate, I had to be able to hold it in the vise. A bit of 50mm square bar fit the bill perfectly. Well, it was nearly square. 2 small welds that could be ground off at a later stage is just what the doctor ordered. Here I skimmed up the bottom face and dressed up a couple of end faces. Using the tilting vise, I set the angle to 47 degrees. That'll cut one side of each slot. Then to cut the other side, I had to unclamp the base and then rotate it 180 degrees, put it back in to finish the second side of each slot. It won't be perfect, but it will be close. Close enough to scrape it in later anyway. With the base plate partially machined, I can now mark out for the clamping plates and the associated bolt holes. I'm setting the hole positions to be central to the bedway. You know, if I make a mistake during construction, I could damage the main head spindle bearings. It's possible that the pedestal may not be stable or rigid enough, and if the overall spindle length is too long, it could cause secondary torque-induced vibration, but we'll have to see. I've used 10mm plate for the swivel clamps. The clamps will have a radius cut into the lead edge so that when the bolts are done up or undone, the clamp plates should align themselves to the right position to save having to manually hold them in place while using the Allen key. I'm drilling and tapping for 12mm cap head bolts. By holding the bearing case in the 3-jaw chuck, I confirmed that everything was in the right place. Because the base plate wouldn't quite go under the supports until I slacked the jaws off a little bit, and this allowed it to slip under, and then it could be clamped in place for tack welding, then final welding. This is the unit after it was welded. I missed the scraping out because it was so boring. I almost fell asleep watching the footage. Now I can't have you nodding off before you get to the exciting bit, can I? As to say, I spent several days getting this bit done, and now it sticks to the main slide if there's the slightest bit of oil or engineer's blue on there. For those of you that have seen my tailstock repair video, you'll recognise this setup, but I'm going to have to pull a couple of rabbits out of the hat here. My plan is to rough machine the bearing recess on the tailstock side of the pedestal first, then rough and finish the bearing recess on the chuck side before returning to the tailstock side and finishing that. However, the setup, unlike the tailstock repair, the cutter will be quite a long stuck out affair, so the cuts I make will have to be fine cuts. With the cap head screws in place and tight, it's time to get on with it. The tailstock side of the bearing head is easy to measure. You just simply slide the line boring bar out and then use a stick mic. But the chuck side is going to need a little bit of old-fashioned divider work and a lot of patience. Setting the cutter is really quite easy. One simply takes a cut and then measure it to discover how much to take off next time, as always. But to set the tool, you use a DTI to find out in space where the tip is. You slack off the grub screw and tap on the amount you require. Then tighten up the grub screw, But before you do anything else, confirm that that setting is correct by passing it over the DTI once more. Simple. This is a 5mm square high-speed steel blank. It's been ground by hand to the shape I want. The measuring system on the chuck side is the same as before, except that the boring bar can't be removed. So I use my dividers as a reach over stick mic. Then I compared it through my micrometer. One obviously needs a very light touch for this. When I was satisfied that the chuck side was finished, it was time to finish the bore on the tailstock side. After I'd removed the pedestal from the lathe, I remeasured both bores on the workbench and they were both within 0.005mm of each other. That was good. Fitting the bearing outer races was fairly easy, but to be on the safe side I used some Loctite 638 on the seatings and pressed them home very quickly. At this point I'd almost forgot to put a grease nipple in. I marked out, then I drilled and tapped for a 6mm nipple and set it in place. I'm making the main spindle from two parts, and these two parts are going to be pressed together and welded for a bit more security. Obviously this 50mm diameter bit is the internal part of the spindle, and it's going to be the datum component by means of centre holes at each end. The centre holes are what tie the whole spindle to the bearings and by default to the pedestal. Now I'm machining a 125 by 20mm bar end. This will be the chuck support. This is the second part of the main spindle. Both parts have had a small lead machined in them to aid the assembly during the press operation. These two parts are also externally welded after they're pressed together. This is a quick confirmation that the spindle will actually fit my spindle grinding attachment. Now the spindle roughing operation can begin. However, The speeders had to be kept below 400 RPM due to the out of balance forces on the drive plate, despite fitting a counterbalance. As you can see, I'm cleaning up the OD and roughing the chuck spigot. For me to be able to turn the spindle round the other way, I need a method to drive it from the drive plate. If I'd got one of those big dog drives, I could use that, but I'll stick to the cheaper option of drilling holes. These holes will eventually be used to bolt the chuck on, so they'll need to be in the right place. And before you start commenting about the apparent freehand drilling, I can assure you it was done in a floating vise. Now I can concentrate on rough machining the second operation of this spindle. Now the central spindle was turned down to 45.75mm to leave plenty on for final finishing. This is the thread relief groove, and this is the 3-jaw bite area. This stainless steel sleeve was made using a bit of scrap drive shaft, as you can see here. The sleeve is going to be cut into 2 parts, and the remainder is going to be internally threaded and used as a temporary locking collar for final finishing. I had to be very careful here because the workpiece was held very lightly. That was in order to maintain bore concentricity. Inside the bore I cut a 15mm wide recess to reduce the load and unload friction. And as you can imagine, parting off the 58mm long sleeve needed to be handled with the utmost care. The remaining collar that was left was internally threaded to 45mm by 1.5mm pitch before I returned the sleeve back to the chuck and faced each end. The spindle was finally finished to 45.2mm from measurements taken from the sleeve bore, and that was only after it was left to settle overnight. Even then the spindle had to have a quick wipe with emery cloth after every cut to make sure the mating faces were nice and clean. After that I could finish off the bearing face and the oil seal spigot. The 45mm diameter by 1.5mm pitch spindle thread was cut using my external thread cutting tool. After both components had settled overnight, I retried them once more and the fit is just wonderful. In order to hold the spindle in place I need a nut, and in order to prevent it from coming undone, that means I need 2 nuts. My plan was to make the first nut part of the oil seal, and because it would have been so big, milling flats on it and using spanners wasn't really practical. So I opted for discs with radially drilled 4mm holes in each one, so I can lock and unlock them using dowels. In turn meant that there are no edges to catch things. This is where I finished machine the spindle sleeve bearing diameter. And in order to prevent it spinning on the spindle, I put a rubber O-ring at both ends of the sleeve and locked it in place using the threaded collar I made earlier. The bearing bore is 55mm, so I need the sleeve outside diameter to be 55mm plus 0.01 to plus 0.02mm after grinding. I'm glad I had this grinder attachment. Even with 24 volts, it still laboured when the full cut was attained. Mission accomplished. This is where I machined both the locking nuts down to 100mm diameter, that's flush with the bearing case. And I also finished the oil recesses. Both ends of the bearing cage has a 90mm by 4mm deep recess in them, so both the oil seal spigots were machined to 89.7mm. Hopefully not too much dust will get in there. To drill the holes on the chuck backplate, I used the indexing table to get the holes in the right place. The spindle was set on it using the DTI mounted on the base of the indexing table. I bought another 4-jaw chuck so that I could permanently leave it on. But after a Doc Emmett Brown moment, I realised that in the future I might want to mount the 3-jaw chuck. So while the holes for the 4-jaw chuck were going in, I might as well drill the holes for the 3-jaw chuck at the same time. This was a very satisfying moment. The sleeve that had been designed to hold the bearings in place had to be pressed into place, but without having to have too much pressure exerted on it. It was just about right. In an effort to make sure that any run-out, however small, was reduced as much as possible, I scored a line down the spindle and put a punch mark in the sleeve face at both ends. This is to ensure that the spindle always remained in the same position relative to the sleeve. Putting the 4 radial holes in each of these 2 lock nuts is a basically straightforward process and doesn't really need any explanation. There is a plus side to this system because for the most part the 4-jaw chuck mostly handles short and irregular components, and is better suited to the position of this adaptation most of the way up the slide, if you like. It'll certainly be quicker at swapping the chocks. And being reversible means that I can put it at the tailstock end of the machine and firmly hold awkward components, which I'll show you in a moment. I've also realised that this unit can also be mounted on the tool cutter grinder for a whole new experience in grinding faces and larger objects. This bit didn't quite go to plan. What I'm doing here is gluing some felt rings to try and further reduce any bearing contamination. The chuck side worked fine, but the locking side lasted about 2 minutes and it jumped out at me like a red maggot. This is where I'd finished pumping it full of grease. The last bit of this project that needs to be machined. The spigot is the same for the 4-jaw as it is for the 3-jaw. That was lucky. I'm going to have to modify one of my Allen keys to fit under the chuck here. To machine the chuck spigot, fortunately I had a long piece of high-speed steel bar, 12mm square, and after a minute or two taking chunks out of one of my knuckles on the pedestal grinder, I had the ideal tool to reach over the extended gap where there would ordinarily be a chuck. That was a nice fit. Now all I've got to do is just deburr it. This exercise was basically to see if I could put the chuck on and indeed take it off without having to dismantle the pedestal, and I can. Here I put a bit of irregular shaped material in the 4-jaw chuck and machined a bit off the face. It wasn't a heavy cut, it wasn't a particularly big cut at all, but it worked, and it worked well. Removing this 4-jaw chuck took me 45 seconds. It normally takes me about 5 to 10 minutes, and what is more, I can leave this set up. Swapping the chuck round in the pedestal took me 1 minute 50 seconds. This is going to give me a few interesting options. That's all for now. Thanks for watching. Bye.